Hi, in this video I'm going to talk about Ethereum Virtual Machine model, and I split this video into two parts. So let us start with the first part. In this part, I will explain what does it mean by decentralization plus permanence equals the blockchain 2.0, technical background of Ethereum, accounts, externally owned accounts, transactions, BNB transfer transactions, and contract addresses. So let us first compare blockchain 1.0 and 2.0. Blockchain 1.0 refers to the emergence of Bitcoin and its underlying blockchain technology, which enables the transfer of value without the need for a central authority. Blockchain 2.0 is the introduction of smart contracts, which has enabled the creation of decentralized applications on blockchain networks. As the example of blockchain 1.0, we can give Bitcoin, and for blockchain 2.0, we can give Ethereum and BNB chain. So in this regard, decentralization refers to the distribution of power, authority, or function among multiple parties, rather than having a single central authority in the context of blockchain. This means that the network is maintained and secured by a decentralized network of nodes rather than a single central entity. Permanence refers to the idea that once data is added to a blockchain, it cannot be altered or deleted, and this provides a secure and permanent record of transactions. So the phrase decentralization plus permanence equals blockchain 2.0 could imply that the combination of these two features creates a new and improved version of blockchain technology, which is blockchain 2.0. So let us see technical background of Ethereum. Blockchain networks are made up of nodes. In an Ethereum Virtual Machine compatible blockchain, these nodes run a virtual machine called the EVM on their own network. For example, we have a decentralized system and a pyramid here. So let us talk about this. Basically, we have nodes, and every node can run an instance of EVM. And using these EVMs, we can create our smart contracts. And these smart contracts can be used to create decentralized applications. So let us understand accounts. Accounts represents the location on the Ethereum virtual machine. There are two types of addresses. The first one is externally owned accounts. These are addresses that are controlled by a private key. They are used to send transactions such as transferring BNB and interacting with smart contracts. Contract addresses. A contract address on BNB smart chain represents a smart contract that has been deployed on the blockchain. Each smart contract is given a unique address, which allows for interaction with contract, including calling its functions and accessing data stored on it. So let us see states of an address. So in an address, we have balance, nonce, code, and storage. The balance keeps the amount of native tokens that owned by the user. Nonce value, it's the count the number of transactions the user has performed. Code is available only at smart contract addresses. The compiled smart contract bytecode is placed in this state. Storage is available only at smart contract addresses as well. The data associated with the smart contract is kept here. So in external owned accounts, we have this description, right? What I mentioned was we have a private key, and this private key is generated with the ECDSA algorithm. You don't need to know about this algorithm, but it's better if you can understand the logic behind it. You can search for it on the internet. It has a lot of details, but it is basically an algorithm that you can generate your private key. So from this private key, we can create a public key. The public key is derived using the private key itself. It's used to check the authenticity of the signatures sent to the blockchain. And the important thing here, we can't get the private key from this public key. We also have public address. It's used to generate the EVM address. It represents the point at which a user stores their funds. Public address is needed when sending money to someone. And we can't also get this from the public key as well. So here, externally owned accounts are addresses that do not contain code and storage and are used by users to send money, receive money, and perform transactions. These addresses have only balance and nonce states. Code and storage values are 0. Here, when we want to see our address, we have some states, right? For example, we have this address. It's not important here. It can be any address. It can be your own address as well. So balance, for example, it can be 1.5 BNB. And nonce value, which is the count of transactions, is, for example, 52. And the code and storage values should be 0. So let us see transactions. Transactions in Ethereum Virtual Machine are messages sent from one address to another address. Transactions provide state updates on the EVM, which is very important to understand. For example, here we have an address, and I want to send a transaction to another address on the BNB chain network. So these transactions on the BNB chain network are initiated by signing them with a private key. The corresponding public key is then used to verify the authenticity of the signature, ensuring that the transaction was indeed sent by the owner of the private key. So this transaction can be used to transfer transactions, execute smart contracts, to deploy smart contracts, and to interact with decentralized applications. So what does a transaction consist of? In a transaction, we have a from property, which is the address of sender. We have to property, it's the address of receiver. We have value, it's the native token that is sent with transaction. Nonce, it's the nonce value of sender address. As I mentioned, it's the count of all the transactions. So timestamp is the time at which the transaction is sent. We also have gas limit. It's the maximum gas limit for a transaction. Gas price is the fee the transaction sender is willing to pay per gas. We also have VRS. It's the signature information of the transaction sender. We have data. It's the bytecode that is moved here in contract deployments. Parameters sent when running smart contract functions are also carried here. So let us see BNB transfer transactions. So I will explain a scenario below. And in this scenario, a Binance coin BNB transfer is made between two externally owned accounts. The states of the sender and receiver addresses are updated, and the nonce value of the sender is incremented by 1 to prevent double spending attacks. Let us have an account here. And in this account, we have the balance of 0.5 BNB, and our nonce value is 52. And I want to send 0.3 BNB to another account. And in this account, our balance is 0 BNB. So since we have a transaction here, the nonce value of the first account will be incremented by 1. And as a result of this transaction, we have 0.2 BNB here. And our nonce value is incremented by 1, meaning that our nonce value is 53 now. Since we have sent 0.3 BNB to another account, the balance of this account will be 0.3 BNB. And the nonce value will not change since the receiving address did not send a transaction. Alright, so let us see contract addresses. Upon the completion of a smart contract, bytecode is generated. Bytecode is a low-level instruction set generated from source code written in a higher-level language, for example, Solidity. In the next part of this course, we will create our own smart contracts, and I will also show you the bytecode of our smart contracts. It's not a meaningful code. We basically write our code in a programming language, like I mentioned, for example, Solidity, and these codes will be converted into bytecode. So a unique address is generated by passing the bytecode, sender address, and the nonce value of the sender address through a hash function. A contract creation transaction is then sent to this address. For example, I have a smart contract source file, and in this smart contract, I can have any functions that can create my decentralized application. Then it's going to be compiled and it will be converted into bytecode. Then this bytecode will get into a contract creation transaction, and we'll have an address here which has the properties of balance, nonce, code, and storage. When we have all of these processes, the bytecode of the contract is included in the data field of the transaction. Once the transaction is confirmed, the code state of the address is updated, effectively deploying the smart contract to the designated address. And for example, at the end of this process, we have an address, and for example, this is our address here, and we'll have a balance at the end of the transaction. The nonce value, for example, 98 here, but it can be anything. It's a random number, just to explain. And we'll have a code which stores the bytecode, and the storage which stores the data associated with the smart contract. All right, that's gonna do it for this video. I will see you in the part 2 of EVM model.